Before I dive into some more derivations today, are there any questions on the coding part of the class? I know not all of you are participating in that, but the BYU students are. It's a big part of their experience here. So what were you able to get the package, the Julia package? I'm curious, and download it. And
so Mike, I was able to get the Julia package downloaded eventually. For some reason, it was saying I didn't have permissions until I sent it to desktop from the website, and then it was able to do it. But once I've pulled it down, I've tried starting it up, and I've been having issues with, it's probably just a Windows problem, but I eventually got the path to load correctly so that I could start Julia from a command or a PowerShell window. But even though I do that and it uses that current working directory as the working directory for Julia when I open it the way you were asking us to in your prompt with inside Git, the activate won't activate the environment variable in the working directory, the current working directory. It goes to the, I don't know why it keeps pointing back to the original working directory or the main directory of Julia. Is there a way to force it to activate your environment variables there in the working directory?
you type activate dot, and the dot tells it in that directory. You have to make sure, sometimes Julia will start up in weird places. You can go to a shell prompt inside the Julia replicator and change the directory and then type activate dot.
So the directory I have, so if I do pwd, it tells me I'm in the working directory, and I tried activate dot and it's still not working. Is it just activate space dot or what?
Activate space dot, and it will read the a file in that directory.
Okay, that worked. Thank you.
Oh, we fixed it? Wow,
yeah,
great. Okay.
I couldn't find the space dot in the documentation. I'm sure it's there somewhere.
It is, yeah. Okay, so any other problems from the students doing this?
My next problem after you get past the dot point is how to install plots.
You just type import plots.
Okay. I think I've been trying that and it hasn't been working.
For me, when I was in the package, you know, you hit the right square bracket to get into the package state.
Mm-hmm.
If you type instantiate while you're there, it will install all the Julia packages you need for Core4MyGA. So that's plots and all of its dependencies.
Oh, interesting. Maybe I need to add that to the documentation. Thank you, Caleb.
Yeah, so I had to do that before it would work.
Okay. Yeah, so when you go into the package part, type instantiate, and then you probably should see a whole bunch of things download and install.
Cool. I'll try that then.
Okay. So for those of you who are taking the course for credit, I'm going to post the final project for the course in the next few days, and it's going to have something to do with solving a flex problem for a little axial rod. And I may have you select a problem of your choice, and then I'll say I want a certain output. So I still want you to go through the process of creating as much of the code as you can. The Julia package really is just for reference. It's important that you have that experience. I hope this speeds it up. So that's still going to be a requirement. Any questions on that? Okay, great. Well, let's dive in. All right, so we've been talking about this method where we've got weak enforcement of the constraints through a Lagrange multiplier. And we started with the following energy functional. Let me write it down here. Can you guys see my screen? The whiteboard here that I'm drawing on?
Yeah, we see the whiteboard.
Okay, so we started with this. So this is the elastic energy. Omega. So this is the strain energy here. And then we've got some body forces, external forces. Minus gamma CH, these are the tractions. Okay, and then we have some additional terms that come from the displacement constraint. Let me denote these by pi d u lambda. And what I've given you so far is the following, where we're going to enforce the constraint through a Lagrange multiplier. Okay, and then this leads to a matrix equation. This all leads to a matrix equation that looks like this, where we have K B transpose B 0. Then our unknown variables, D and lambda. And then this is going to be our F and our G. Okay, so this K here comes from discretizing the weak form associated with this. So let me write that down real quick. So the weak form associated with this guy is okay, and then we discretize this and put it in to this slot right here, this K. If you think back to the mathematical stuff that we studied with regards to norms and semi-norms and spaces and all of that, can somebody identify for me what this is in the terminology of the mathematics that we studied? What would we call this? Yeah.
It looks like an L2 norm, I guess, with
Okay,
an EA in it.
Yeah, you're really close. Okay, yeah. So it is, let me write, I'm trying to have to move some Zoom bars out of my way. Zoom just like splatters stuff all over my screen. And then they make it almost impossible to grab it and move it. Okay, so if you remember, the L2 norm was, and this EA, let's just set, just for simplicity, it's just a weighting, but let's just set it to 1 for simplicity. Okay, so the L2 norm, let's maybe say the L2 inner product instead of the norm. The L2 inner product is going to be like, it would be delta U d omega. Okay, so that's the L2 inner product. The H1 inner product is delta U plus delta U comma X, U comma X. And then if you go ahead and you take the let's see, so then the norm that's associated with the L2 inner product, all that you, so the notation we use for the inner product would be delta U, and then the norm associated with this guy which we denote by U, is nothing more than putting U in both slots and taking the square root. Okay, and similar here, and sometimes we'll put like a 2, like an L2 down here, and for this one we would put like an H1. Okay, so so you see up here we have a delta U comma X, delta U comma X. Do you see how it maps to this guy down here? So it's just a piece of the norm, of the inner product, sorry. It's just the derivative piece. But we do not have this standard L2 piece here. So what are the consequences of this? If you just have, in fact, we have a name for this. If we were to view this as a norm, we would call this a semi-norm because it's semi-complete, right? It doesn't have everything that the inner product should give us. Anybody know what the consequences are of, so in other words, this strain energy term is basically equivalent to something we would call a semi-norm. And there was a homework problem that I gave you that had the semi-norm, and I talked to you a little bit about null spaces and invertibility. Does anybody recall what we learned in those assignments? Is there anybody on the call still? Let's see. Are there still people on the call?
I'm here, Dr. Scott.
Okay.
I'm just trying to remember, honestly. I'm going back and looking at the homework assignment.
Well, does anybody know, just offhand from using finite elements, what's the problem if you just discretized the strain energy without boundary conditions? What would happen? The suspense is...
Just kind of go off into infinity, right? There'd be nothing.
What's that?
It would just kind of go off into infinity because you're not really solving in the space where the solution is.
Yeah, that's exactly right. This is a semi-norm, which means that when you discretize it, what's going to happen to K? So K is now the discretization essentially of a semi-norm, this incomplete inner product. So what's going to happen to K, this matrix? What do you think will be one of the properties of K?
I'm going to take a guess here and saying that since the null space is non-trivial, it's going to be not invertible.
That's exactly right. Thank you, Kaylin. In other words, I've given you a method where this part of the matrix, if you just look at it by itself, this K matrix is actually not invertible. Okay, so that's kind of not very pleasing, right? You still may be okay if your B matrix is non-singular because you're going to end up kind of solving the entire system. But what that means is you can only solve this system. It's called a saddle point system because of the way that the structure of the matrix. You can only solve it now using basically a monolithic scheme. In other words, you have to solve, maybe we call this big matrix A. You have to solve it by inverting big A, right? Like the whole thing. Whereas most of the time with these kinds of systems, you're going to want to segregate them. And those segregated methods are often going to require the inverse of K. And so the formulation that I've given you so far, where you have the strain energy, but there's no strong boundary conditions, right? The boundary conditions are being enforced through a Lagrange multiplier, is going to lead to a stiffness that's singular. And so that will greatly limit both the algorithms that we can use to solve for the solution, and it will also deteriorate the conditioning of our problem, making it more difficult to solve. Okay, so what we want to do is we want to now come back to this method and we want to do something with this energy here in order to correct the deficiencies in kind of a vanilla mixed or saddle point problem. Okay, so we want to kind of come back to this and clean it up. So let me erase a bunch of stuff and we'll do that. So what we're going to do is we're going to create an augmentation of our method that doesn't change the minimizers. So we'll get the same solution, but it will be more convex. In other words, it'll be easier to solve. It'll have more of a stronger kind of quadratic characteristic to the problem. So when we try and minimize it through differentiation, it'll be easier for us to find the solution. And this is a whole class of methods that are used everywhere. In fact, you'll see them in optimization, you'll see them in finite elements. In finite elements, you often see them and then they're like, have different names that will pop up and you won't realize that they come from the same place, but they in fact do. And what we want to do is we want to create what's called we want to take our Lagrangian, which is this guy because it has the Lagrange multipliers, and we want to augment it. So it's called an augmented Lagrangian method. And what we're going to do is we're going to add a penalty term on to this pi d that essentially says, I want to enforce the constraint. In other words, it's just like this guy, right? But notice that it's quadratic now. Okay, it's quadratic and it does not involve lambda. See, lambda's over here, and if we return to our linear system, A, B transpose 0, we know that this term here will give rise to our B. But we know that it our K might be messed up. But this term here, this quadratic term, notice that it doesn't change the minimum, right? The minimum is U equal to U naught. Well, this is also enforcing U equal to U naught. So you essentially have more energy. You have greater possibility. You'll enforce the constraint better by adding this augmentation. So you don't change the problem, but it adds this nice quadratic term. And this quadratic term now is going to give rise to essentially a mass matrix on the constrained boundary. Okay, and can anybody guess where when we discretize this into a mass matrix, let's call it M, where it will end up in this linear system? Where do you think it will end up by looking at the variables that are involved? Is it going to end up down here? Is it going to end up here? Where's it going to end up?
I'm guessing somewhere to the top left of K.
Yeah, in fact, it's going to fix our K, make it much better conditioned and non-singular. So what the augmentation does is it adds a mass matrix on the boundary that will remove, when you add K to M, this matrix now will be both better conditioned and non-singular, regardless of whether you have any boundary condition constraints at all. In other words, it kind of removes the null space up here. Okay, and so this is a very nice and important addition. And with smooth splines, just to give you a little bit of perspective on this, with IGA and smooth splines, all the methods are moving to these like non-body fitted methods. Okay, and as we've discussed at length, the reason for that is because with the higher order splines, you get even superior accuracy, you get really superior accuracy even in this regime of problems. And so why wouldn't you do this, right? It simplifies things. It simplifies the model building process, but it can introduce, if you're not careful, if you don't write down the appropriate formulation, you can get these problems that pop up in your linear systems because you don't have the classical enforcement of boundary conditions, right? There's no nodes that you're setting to values. You're solving for that constraint as part of the solution procedure. Okay, and so in IGA and smooth splines, if you read the literature, what you'll find is that there has been a proliferation of methods that are looking at how to, what we call weakly enforce constraints. And what I want to do now is, so let's label this guy. This is called an augmented Lagrangian. And what I would say is this is kind of our starting point. This is our most general, sometimes it's just abbreviated AL. I'm curious, any of our engineer or industry folks that are with us, anybody used an augmented Lagrangian formulation, maybe in a problem that you've solved?
Would they use augmented Lagrangian in the Uinta code?
I don't know. I don't know what the Uinta code is. Let's see. Anybody solved an augmented Lagrangian problem? Maybe the answer is no, and that's okay.
Yeah, I guess we have been using that for contact enforcement in Moose.
Okay, perfect. So who was that just mentioned that?
This is Wen Jiang speaking.
Yeah, okay, perfect. Yeah, so in Moose, which is a code at Idaho National Lab, they have a constraint called a contact constraint that is just, they replace basically this term with something slightly more complicated that's appropriate for contact. And they do, in order to do implicit contact, which requires the formation of this full stiffness matrix here, they will often use augmented Lagrangian for the exact same reasons, to improve the robustness of their contact algorithms. And it's nothing more than replacing this constraint here with something appropriate for contact. But the structure of the matrix is the same. Nothing changes there. So let's, I appreciate when you sharing that. That's an important application. Contact is a big one because contact is hard. And so you end up seeing these very robust methods, these full methods like augmented Lagrangian being used in that context. Okay, so now what I want to do is show you how several classical methods that in particular you'll see in some of the older codes, you'll see also in the IGA community, can all be derived from the augmented Lagrangian framework. And this is helpful because if you read the literature, it is a little daunting because you don't have any idea how these methods are related or where they come from. And this will hopefully help eliminate that confusion. So let's take a look at this method here. Let me clear my screen and this over again. So we've got okay. So the energy coming from the so the total energy, let's say, is going to be the energy coming from kind of the elastic part plus the energy required to enforce our displacement constraints. Move a zoom toolbar again here. Okay. And so in all of these methods, this is another important point. This guy is unchanged. This is our standard weak form for elasticity, and it remains unchanged. We're just focused on this term here. So what I've said is that in the augmented Lagrangian setting, which is kind of our general framework, we've got our Lagrange multiplier term, lambda u minus u naught. And then we've got this augmentation here, which is just a penalty term. Okay, so now let's look at some other methods. Let's say I delete this guy. If I delete this guy and I enforce the constraint just with this second term, does anybody know the name of those, what we call those methods?
Deficient Lagrangian?
Just a penalty method?
Yep, this is just the penalty method. So if you've ever used a penalty method, which I would, this is
They do that in
very,
contact a lot.
that's right. So a penalty method is a very, so I would call this the engineering approach to enforcing constraints, meaning there's like a very classical way to interpret this term. And let me add one. Usually there's a, we divide by 2 because when we take the derivative, this 2 comes down. So if you just put your engineering hat on and let's say you look at this term, what is it? Like just, we have some, so it's force times distance squared. Then we'll integrate, which will get rid of one of the distance. So this is like a force times a distance. What is this basically a model for? What is this penalty term basically a model for?
Force for overclosure?
It's just a spring. So in other words, we're saying, let's model let's model the enforcement of a constraint by basically a spring constant. That's what the penalty is. Times basically how much the spring has been stretched, which is how far away it is from enforcing the constraint. So you can see why the penalty method is so popular, right? I mean, it's probably, I would say, if you look at industrial codes, it is probably the most common way to enforce a constraint, because it's just like basically attaching springs to everything, and you're like attaching springs to all the nodes, right? And measuring how far those nodes are away from enforcing the constraint times your spring constant gives you the force, the rectifying force that you're trying to minimize. So the linear system, another reason that the penalty method is very nice is, notice we've eliminated the Lagrange multipliers. So what does our linear system look like now? Well, we started out with K plus M, B transpose B, 0. Which is a mixed, we call this a mixed problem because you have both Lagrange multipliers that you're solving for and displacements. And now we've gone to what? What's left? Well, just the K plus M. So now we're left with a method that is written just in terms of our displacement degrees of freedom. So we've reduced the size of our problem, and we've added this basically this type of mass matrix to K. But what what's the drawback here? So
is this what they're using when they're doing paradynamics? Is this, because this looks very similar to the math behind the paradynamics code.
yeah, again, I don't know the details on what they've done there. I mean,
Okay.
the penalty method is everywhere, so you'll see it everywhere. It's usually this, it's like the simplest way to enforce a constraint, both from a conceptual point of view as well as an implementation point of view. So you see it a lot.
I guess, yeah, like atomistic modeling type equations is what I'm kind of talking about, but okay.
Okay, so what is the problem with this, though, is the question that I have. So if you wanted to enforce the constraint, yeah, so if you wanted to enforce this constraint exactly, so if you wanted u minus u naught to be 0, how big would your spring constant have to be?
Infinite.
That's right. So in order for you to get exact satisfaction of your constraint, this penalty term has to go huge, has to become huge, which means that the entries of M are going to be much bigger than the entries of K. So when you add them together, you're going to get a matrix that has small entries and really large entries. And what will be the implications of that?
Or conditioning.
Or conditioning. That's right.
Well, another complication that arises with using the penalty method, and it's just from generally using it, is that it's very difficult to validate because, like you said, you want to be able to enforce a certain boundary, and then you don't really know where your boundaries are actually in appropriate contact, or where they've overclosed, or where they're so far away from each other they really haven't even touched. And so validating that model is extremely difficult as well.
Yeah, so that's a very good practical point of view, that you can't pick a big penalty. Usually you want your penalty to be somewhat on the order of your Young's modulus of your material. That's kind of just a rule of thumb. And if you do that, you will not perfectly satisfy your constraints. And so then the question is, well, what problem am I really solving? In other words, the penalty method, we say, is not consistent, in the sense that if you were to derive the strong form for the penalty method, what you would see is that there's no natural enforcement, it doesn't match like the standard strong form that you would expect, in the sense that u equals u naught. You'd have this penalty that had to be like this infinite value in order for that to happen. So we say that this is not a consistent method. And but nevertheless, I would say it is the most popular method because of its simplicity. Okay, it has some good things going for it. It eliminates the Lagrange multiplier degrees of freedom, which is good. It will eliminate the singularity and the stiffness if you don't have any kind of pin nodes or strong enforcement of boundary conditions. So that will do that, but at the cost of really bad conditioning. So if you're using this kind of in a setting where you have to invert this matrix, that can be very problematic. And the other thing is, if you're solving this using some kind of an iterative scheme, then you're going to need a lot of iterations because of the poor conditioning. Okay. All right, so that's one. So we like the penalty method because it reduces the size of the system and makes it a one field problem. But the conditioning stinks. So the full augmented Lagrangian method is really nice because you'll get exact enforcement of constraints. And because you have a force associated with the Lagrange multiplier, the penalty term that you give can be usually it's almost problem independent, meaning that it can be of a fairly small value. And so this penalty term, if you couple it with the Lagrange multiplier term, will not create the same conditioning problems, which is why it's often used in contact, because it provides some stability to that problem of conditioning. Okay, but we don't like it because we now have like a mixed problem or a saddle point problem where we have these constraint matrices that are involved, and the solution procedures are more difficult now. So what we would like to do is combine the properties of the penalty method with augmented Lagrangian. And that leads to what's called Nitsche's method. Nitsche's method. Nitsche's method. Does anybody know what we do here? It's just a very simple trick that we do. In other words, we need to keep the structure of augmented Lagrangian. We need to keep like its properties, but we have to eliminate lambda somehow, the Lagrange multiplier. So what can we do? Any ideas?
Is this just like the update method where you don't solve for lambda, but you just update it?
No, that's an algorithm. So what you're talking about is like an Uzawa type algorithm, and that Uzawa is simply an iterative approach to solving the full system.
Okay.
Right. Yeah, and that's in the course notes. I talk about this. So it's not eliminating. You're kind of you're essentially kind of updating a residual that depends on the Lagrange multiplier. So it's kind of like a pseudo elimination of lambda, but you still have to solve the k plus m over and over and over again as you iterate.
Right.
So it's just an algorithm associated with augmented Lagrangian type methods.
Could we somehow write lambda in terms of u?
Okay, yeah. So this is Nitsche's idea, is that you say, well, in fact, if you look at the strong form of this problem, what you'll notice is that you can show that lambda should be equal to the traction. So we can go through a very simple derivation. You can show that lambda, physically speaking, when you solve for lambda, it is really the traction force required in order to maintain this constraint. So it's going to basically be some function of the first derivative of the displacement. And so in this simple 1D setting that we've been looking to in class, we'll just set it equal to the negative of the derivative of the displacement. Okay, and that's Nitsche's method, is essentially you say, oh, okay, I have this kind of general framework, augmented Lagrangian, but this whole problem comes from kind of conservation of energy, and so you can identify lambda with an actual physical quantity, the traction. And we know how to write down the traction. It's just the derivative of the displacement, and then there's some material parameters that will give you basically the stress dotted with the normal. Okay, so all that Nitsche's method does is it takes this and comes up here and removes lambda by putting in minus u comma x. Okay, and so now our Lagrange multipliers are replaced by derivatives. And the remarkable thing about this simple substitution is it leads to a consistent, stable method.
Do you lose accuracy when you do that?
No, you preserve accuracy. Yeah, because all you've done is a simple substitution. So it's accurate, has a lot of the same properties as of augmented Lagrangian, but now you still have the same structure as penalty. But now this M guy here involves these two terms, including some gradient quantities here. And then you're going to have another term out. Let's maybe call, I think in the notes I call this H. You're going to have basically this guy is going to be subtracted over to the right-hand side, giving you another forcing vector. Okay, so Nitsche's method is nice because now you've eliminated the Lagrange multipliers, but you have a very physically motivated problem that mathematically is consistent and stable. You still have to give, there's still a parameter, you still have a penalty parameter, but this parameter can actually be estimated through local eigenvalue problems. So you can actually figure out what that parameter has to be. And just like the augmented Lagrangian approach, this penalty parameter will be somewhat problem independent and small. In other words, it will not disrupt the conditioning of the system the way that the pure penalty method does.
So is there any reason not to use Nitsche's method all the time? Like, I'm only hearing pros to it. Are there any cons?
The con for Nitsche's method is that it's complex. Because modeling the traction for complicated problems can be difficult, like for shells and beams. I mean, it's not, I wouldn't say it's like impossible or anything. It's just not as simple as penalty, right? So augmented Lagrangian is fairly simple, except you have this extra Lagrange multiplier. Penalty is very easy because you just simply plug in basically a mass matrix. Nitsche, now you have a little bit of modeling to do because you have to understand what this looks like for your problem. Okay, for our problem, it's trivially simple, but in general, it might be a little more complicated. This penalty now, you still have a parameter. It's somewhat problem independent, but you still have to estimate it. But the only drawback, and in fact, I would say that in the IGA community, Nitsche is now the dominant approach. And so there are literally hundreds of papers now that have been written that are coupling Nitsche's method to smooth splines, because smooth splines are already good for non-body fitted kinds of applications. And Nitsche's method kind of has the robustness of AL with fewer degrees of freedom. But it's more complicated to derive these methods. But if you're already able to like derive all these other methods, you'd think you'd be able to derive this method too. And there's so many new results on Nitsche's that it's, I wouldn't say that that's much of a blocker anymore. And so, yeah, I think that it's either AL or Nitsche's. Penalty is, you know, if you're doing like maybe explicit dynamics or something where there's small geometry changes and you're not looking too closely at like the contact forces or the constraint force enforcement forces, then fine, penalty would be fine. It's also maybe a nice starting point for an implementation, because it's so simple. You can get it up and running and kind of get a feel for things, and then you can implement these, you can layer on top these more sophisticated methodologies. But I would say that, you know, like in our implementation, we favor, at least in the long term, these augmentation methods coupled with some kind of a Uzawa iteration, okay, or a Nitsche type approach where you eliminate it, but you do it in a consistent way. Okay, so in the notes, if you go back and look, I've added this augmentation now to the notes and derived everything in terms of this augmentation. And I also show you the penalty and Nitsche simplifications so that they're there and you can look at them. And Yeah. So any questions on this? Any questions or comments?
Do you know if commercialized codes use Nitsche's method right now? Or is it
Oh, I'm sure some of them do, I would imagine. But it has definitely become much more popular like in the last 5 years within the and it's been driven mostly by the IGA community for sure. So you'll like, I don't think you'll find, like, if you look at the contact algorithms, you might then ask yourself, well, why wouldn't we do Nitsche for contact? Well, that's a good question. It just hasn't really been explored because people kind of stopped at AL and didn't continue. But I think Nitsche for contact is also a fantastic, that's really a research topic, but one that is just beginning to be explored. So any kind of constraint enforcement. The nice thing, though, I will say about AL is, you know, there are other kinds of, this is a very simple displacement constraint where you're just saying, I want the displacement to be equal to some value. This constraint may actually be some complicated nonlinear function of u, right? I mean, there are many kinds of constraints you may want to enforce in a general purpose finite element program. And so the nice thing about the augmented Lagrangian is that it can accommodate basically any kind of linear or nonlinear constraint. And then you just kind of have like a recipe for building the B matrices and adding the M matrix, and you can enforce like any number of constraints. Nitsche's, I would say, is, I mean, you'd be hard pressed to kind of understand what this term would look like for a constraint that is not simply just a displacement, like a spring kind of constraint thing. So Nitsche, I would say, is kind of, it's kind of appropriate if, you know, if you're really trying to come up with a clever way to remove the need to enforce the standard Dirichlet boundary conditions, it's a good approach. But AL still probably is more general purpose, I would say. In other words, you could do almost anything with AL. It's just like turn the crank kind of a thing. So a lot of codes, you know, a lot of the big finite element codes, they have, you know, they may process literally hundreds of different kinds of constraints in a single run. And nobody like has time to sit around and like derive a different method for every single possible constraint you could run into. So that's one issue. But just in the regime of contact, for example, when you know the constraint is a contact type constraint, then I would say the Nitsche's is a very favorable, a very nice way to think about enforcing that constraint, because you know what that constraint's going to be. Okay, so that kind of gives you a 10,000-foot view of where spline-based simulation is in the enforcement of boundary conditions. Of course, there are approaches where you simply set nodal values. That still is done as well. So that's just a standard approach, and that is still a part of the toolbox that you have available to you as well. Okay, well, I'll stop there if there's no questions, and I can stay on the line for a few more minutes if you want to have any follow-up discussions. But thanks, everybody.
Thank you.
So Dr. Scott, in the Nitsche's method, lambda, when you're replacing lambda with the traction, that's not just an approximation. I mean, you're deriving it exactly and then replacing it, right?
Yes. So on Friday, BYU students, bring your codes. I'll send out an email about that.
Sounds good. Thank you.
Yep.